Okay, welcome to the first of my videos to cover this final external for level 3 chemistry called aqueous systems. It doesn't have a very inspiring title, but as the name suggests, it's all about particles which are dissolved in water. And there's four sections that I've identified in this topic. The first one being what is an aqueous system, and I covered this in 1 week in school, so it's quite short, but you need to have a good understanding of the concept to an aqueous system. Number two is then acids and bases, so there'll be a little bit of a review of what you covered with strong acids and bases from level 2, and then for level 3 there's particular focus on weak acids and weak bases as they set up an aqueous equilibrium. Then coming off the understanding of weak acids and bases, you can form buffers, which have an integral role to play in the generation of titration curves. So section 3 will be titration curves and buffers, and then number 4, the final section, will be relative solubility of these solids in aqueous solutions, and you measure that using Ks and S. So section 1 we covered this week, what is an aqueous system? Well, to simply define an aqueous system, I like to use the 4 S's, where each of the S's stand for one of the components of the system. So first S is the solid component that you're dissolving in the water, and the two solids of interest are either molecular solids or ionic solids. You covered 4 types of solid in level 2 chemistry. You covered molecular solids, ionic solids, metallic solids, and also covalent network solids. But of interest here, we're just focusing on molecular and ionic. Then the solute solvent, of course, is water, hence this topic being known as aqueous systems. So aqueous is another word for water. And then the solvent with the solute dissolved will eventually form a solution, which is also known as our aqueous system. And then the fourth S is just to remind you guys that if a saturated system is established, then you have what's known as an equilibrium. And then if you have an equilibrium, then there are some things that we can state about an equilibrium. And the first one being that the forward rate of production of products equals the reverse rate of reformation of reactants. So that's the first thing about a system in equilibrium. The second thing is that there's no observable change. No observable change in a system at equilibrium. And the third thing is that it's constantly forming products and reforming reactants, so it's constantly changing. So this is known as being a dynamic equilibrium, and that's a little bit of a reminder from your level 2 chemical reactivity as well. So try to draw the links all the time between what you learned in level 2 and what you're going to need now for this level 3. But they're the 4 S's, which are the best way to describe what is an aqueous system. So if we pay particular focus to the 2 types of solid here, so molecular solid or ionic solid, and we'll just give a brief overview conceptually of how these 2 systems are established. Okay, so sometimes it's quite difficult for students to conceptualize what we're talking about here. So I find the best way is to just literally try and draw a picture. So we're talking about dissolving a molecular solid, and the molecular solid of choice here is going to be glucose, which is C6H12O6, as we all remember from junior photosynthesis or respiration. We're comparing that then to an ionic solid, and a good example of that could be just HCl, solid HCl. You're going to dissolve both of these in water. So the physical states are very important when you're writing these equations, and I tend to tell my students to just always include physical states no matter what area of chemistry we're looking at. I'm going to use a blue here now for the aqueous solvent. So that's our H2O, which is our solvent. So that's one of the S's of the system. The glucose is our solute, and we hopefully form a solution then from that. So again, this is H2O. Okay, now we got to think about what's happening at the molecular level when we add these solutes to our solvents. So we're just going to draw in, this is a spatula in both cases. dropping it into our aqueous solvent. Over here we have some solid HCl, if that were possible to get your hands on, and we're again dropping it into our H2O solvent. Now what happens after this point is quite different for both solids in question. For the molecular solid, it's dissolving, so I'm sure you've all seen a nice large cube of sugar get smaller as it dissolves in water, but it's dissolving, not dissociating. And remember, dissociation is when an ionic compound splits up into its component ions because of the activity of water. So because there's no ions formed, this system will be pH neutral, and it will have no electrical conductivity. No electrical conductivity. So molecular solids or molecular aqueous systems tend not to be very interesting, and you might get a small question on your exam paper just to get you to rank some of the species in solution. But outside of that, because they don't affect the pH and there's no electrical conductivity, there's not many questions that you can be assessed on. Whereas if you're looking at ionic solids in solution, there is a lot more to talk about. So for strong acids such as HCl, you have full dissociation. And we're using the word dissociation here and not dissolving, because dissociation involves the ions breaking up. So the ionic compound breaks up into its component ions. And I'll just do this briefly for one of the ions. So the water wedge model states that water will form little wedges in solution. And because of the polar nature of water, it'll be slightly negative down one end and slightly positive down the other. So what it would do is it would completely surround these chloride ions with wedges, and therefore that separates the two ions from each other, which would otherwise be very well bonded together. When you have these ions released in solution, then a couple of things can start happening in the system which are of interest. So you have full dissociation for a strong acid, and that's the water wedge theory. Water wedge theory. Again, that's a level 2 concept. So as a result of full dissociation, the pH is going to be low, and that's due to lots of H3O plus or hydronium ions that form as a result of the H plus H2O. And the other point to make here is that it's a good electrolyte or conductor of electrical current. We did an experiment at the beginning of the week to classify compounds experimentally, so I'll review the findings of that, because there were 6 possible ways to classify compounds or solutes that you're going to add to an aqueous system, and we want to review each of those in detail. Okay, so the first type of compound you can have is known as an ionic compound. The most of these compounds we're talking about are ionic, but to distinguish an ionic compound from something which might be acidic or basic, an ionic compound is pH neutral. Because something like NaCl, for example, if that breaks up in water, you're just going to get Na plus ions, aqueous, plus chloride ions, aqueous, and neither of these species can affect the pH in any way by further reacting with water. So NaCl is a good example of what's known as an ionic compound because it's pH neutral. It would be a good the production of lots of Na plus and Cl minus ions, so it's a good electrolyte. So that's an ionic compound. The second type of compound you can have is described as being molecular. We've just been talking about glucose. So molecular compound composed of non-metal atoms or elements. We just did glucose. You can see there C6H12O6. They're all non-metals. They're also no conduction of electrical current, so they're not conductors. All right, that's molecular. The third type of compound you can have is a strong base. And you came across plenty of strong bases now at this stage in your scientific studies. In junior science, you would have looked at strong base, sodium hydroxide, ionic in nature, because of course sodium hydroxide has both a metal and non-metal component, which is the definition of an ionic compound. So they're ionic in nature, but to distinguish them from simple ionic compounds, they influence the pH by generating relatively a lot of OH minus ions. Okay, so that makes the pH quite high, typically around 12. And also good electrolytes. Good electrolyte. Now the reason you get such a good electrolyte effect from a strong base is because of full dissociation. Full dissociation. The NaOH completely breaks up in water, which can be represented with this simple equation. Complete arrow for full dissociation. That's what the complete arrow means. And then you get sodium ions. You get, if you have 1 mole of sodium hydroxide to start with, we're assuming that you get 1 mole of Na plus ions and 1 mole of Cl minus ions. So full dissociation, great electrolyte, and also really affects the pH of the solution by producing OH minus ions. That's a strong base. Converse to that, you can talk about a weak base, which is really a level 3 concept. So strong base is more of a level 2 concept. Level 3 concept, weak base. Again, ionic in nature, sometimes. Partial dissociation, which is a big difference, dissociation, which simply means only some of it will break up when it meets water. And a good example of that would be sodium ethanoate. Sodium ethanoate is that. If you take that solid and it breaks up, initially it ionizes, that's fine. So it is ionic in nature, and then it ionizes into its ethanoate ion and its sodium plus ion. But what happens next is what influences the pH of the solution, because the ethanoate will further react with the water in the system. So we'll just leave that there. So plus the water in the system sets up a dynamic equilibrium, and it's forming some ethanoic acid plus hydroxide ions, which affects the pH of the solution. So this would be weakly basic. Now, because this system is reversible, you don't get a lot of OH minus ions produced in comparison to a strong base situation, and therefore it's a poor electrolyte, and weakly basic. Okay, that's the 4th type. The 5th type of compound we came across when we did our experimental investigation at the beginning of the week was a strong acid. And a strong acid, when you got a strong acid in your beaker, you get a light bulb will light up really well in a test circuit, and the pH meter will read quite a low reading. Strong acids are ionic in nature as well, but as opposed to the original neutral ionic compounds such as NaCl, a strong acid will produce lots of hydronium ions, H3O plus, in aqueous solution. This is due to a full dissociation. Again, the same idea as for a strong base, so full dissociation, and a great electrolyte. And the best way to illustrate why these things happen is to use equations. So if we take HCl plus water, complete arrow for full dissociation, and you get lots of hydronium ions, and you get your chloride ions. Alright, so that's the strong acid, and the final type of compound that you'll come across in aqueous systems, and these are all the possible systems that you will be describing, is a weak acid. A weak acid system. Weak acid system, again, ionic in nature, produce relatively few hydronium ions in solution. Because of partial dissociation, get used to using that terminology, dissociation, partial dissociation, and then therefore it's going to be a poor electrolyte as well. So in your experiment, your light bulb would have been quite dim to light using a weak acid, such as ammonium chloride. So ammonium It starts off as a solid, you put it into water and it'll break up into its component ions. But the ammonium ion here from the equilibrium system, and that equilibrium system results in the production of some hydronium ions. Some, very few compared to a strong acid, but it does affect the pH slightly. So they are your 6 systems that you're going to come across in terms of describing. Now, what the exam questions do to try and get at your understanding of what's going on inside the system is to get you to rank these species. So you have ammonium chloride species, water molecules, ammonia molecules, hydronium molecules, and they get you to rank these species in order of highest to lowest concentration. And that's how the exam papers try to assess your understanding of the composition of these systems. So the final thing I'm going to talk about now is ranking species in solution. Alright, so the final section for this week in review was ranking these species when they're in solution. Now there are a number of rules, and I had them on a piece of paper for the students in the classroom, but I'll just reiterate them quite succinctly here. The first rule is that water molecules will always dominate. Okay. So despite adding a couple of grams of ammonium chloride here or sodium ethanoate here, that's still never going to come close to the amount of particles we have in the solution. So the concentration of H2O is always going to be number 1. Gets first place. Second thing is you need to identify what type of compound you have. Just come off a page where I did the 6 possible types. So you need to decide, is it an ionic compound, is it a weak acid, a weak base, a strong acid, a strong base, or is it a molecular compound? And that's going to have an influence on how the compound is. And the third thing to consider is the fact that water is constantly equation is H2O sets up an equilibrium with itself where it's constantly breaking up into OH minus ions plus hydronium ions. Alright, and just make sure that's balanced. So you must consider the fact that water will supplement either the hydroxide ion concentration or the hydronium ion concentration depending on whether you have a base or an acid in your system. So they're the main rules for ranking species in solution, and then the best thing is to just look at some specific examples. So here we go for ammonium chloride. So rule number 1 states that water will always dominate in the system. Now what I want to do here is I give students a systematic way to approach doing these, and the first thing we did was we tried to write or draw down a picture to represent what's happening as we wrote our relevant equations. So in both cases you're taking a solid, ammonium chloride, which we can identify as a weak acid in this case, we've just talked about it. Sodium ethanoate was a weak base, so we know we've identified the type of compound, and we're putting it into water when we're ranking species. So here we go. So the first equation you have is to represent the fact that you're adding solid ammonium chloride into water. So that equation is going to be NH4Cl solid plus H2O. We can skip the H2O because it's unchanging. The concentration is considered to be unchanging, so we'll just eliminate the addition of water there. So it's just the complete dissociation of ammonium chloride into its ions in an aqueous system. So NH4 plus aqueous. That's the first equation that happens. So we can represent that in our picture by showing that you have now got NH4 plus ions. Just put a circle around it. So that's one particle, surrounded by the water wedges, of course, and then you've got Cl minus chloride ions again surrounded by the water wedges. So that's the first thing that we can show there. So I'll just get a different color here for highlighting things. So we have NH4 plus right there, and we've Cl minus species to consider as well. Now the next thing that happens, of course, for ammonium chloride being a weak base, or a weak acid rather, is that the NH4 plus uses up a little bit of itself as it reacts with water, sets up that equilibrium, which forms ammonia plus H3O plus ions. Okay, so we have more particles to add to the system now. We already have the ammonium particles in there. The water particles we can always add, though exam questions tend to tell you to ignore the water molecules because they're always there. Um, the ammonia and the hydronium ions we need to add now. So I'll just go back to my black color. So we add some ammonia. That's a particle to consider now, or a species to consider in the system. And the H3O plus is another species to consider in the system as well. And then the final equation, which I tell my students to always write, is the dissociation of water equation. Every single time you're ranking species, you must consider this equation or this process. Make sure it's balanced. We have water already included in the system, so we don't need to add that. We have H3O plus already included in the system, but we do need to add some hydroxide. So the final thing there is we just add some hydroxide ions. So now you can see the total amount of species that you have to rank would be 6 altogether. So 1, 2, 3, 4, 5, 6. So you have 6 different species to rank in this system, and you must rank them in the right order in terms of highest to lowest concentration. So here's the justification for how we do this. Okay, the concentration of water is going to be greatest. That always comes first in your ranking. And the exam papers tend to tell you to ignore water, but I would not ignore the dissociation equation because that's very important. The concentration of water is greatest to start with. Then we want to put the concentration of chloride ions. Okay. So if you think about it, you're adding a couple of grams. Let's say you added 2 grams of ammonium chloride, which is quite, which could be close to, you could work out the moles per liter if you wanted to, be quite high. So you're going to get the same mole. So if we just say, ignore that 2 grams for a second and just say we have 1 mole. So if we have 1 mole of the ammonium chloride to start with, the equation tells us that you get 1 mole of ammonium ions and 1 mole of chloride ions. And then you might say, well, how do we say that the concentration of chloride is greater than the concentration of ammonium? Well, of course, some of the ammonium is further reacted with the water, so that reduces the concentration slightly. So we just leave that in green. So the chloride concentration is slightly greater than the ammonium concentration. Next up, we need to consider the ions. We need to look at the ammonia, we need to look at the hydronium ions, and the hydroxide ions. So 3 more species to consider. Okay, well, again, looking at this second equation, you would think that the concentration of the ammonia and hydronium ions was 6 to 1. But of course, you need to consider the dissociation of water and the fact that this supplements the concentration of those hydronium ions slightly. So I'll do this in red because acidic solutions are associated with red color for litmus paper. The concentration of H3O plus is going to be greater than the concentration of ammonia for the reason that it's supplemented by the hydronium ions from water's dissociation. And then we put poor old hydroxide at the end there. So this accounts for the fact that this is a weakly acidic aqueous system. Okay, so again, if you didn't get the justifications there, just replay the video and hopefully you can listen to me as I explain it. But that is the correct order for ranking those species in solution. Let's look at an opposite scenario, which is a weak base. Same process. So I'll just go back and get black here. So same process again, you must write down the equations and then account for those species in your diagram. So the first thing we're starting off with here is sodium ethanoate, solid. Okay. Your sodium ethanoate, just like before, is going to ionize in the presence of water. So it completely ionizes, that part is okay, into an aqueous system. So ethanoate ions and sodium ions. Alright, so let's add these to our system. Now the solid sodium ethanoate we're not going to add to our system because it immediately dissociates as it hits the water. So what we want to consider is the CH3COO minus, so the ethanoate, that's 1 particle in the solution, and then the sodium ions. So we have 2 species to consider so far, and of course your H2O is always ever present. The next equation then is the ethanoate sets up its own equilibrium with water. So reacting with water sets up an equilibrium and it forms the ethanoic acid plus some hydroxide ions. So in this case we have a slight excess of hydroxide ions, which accounts for the fact that it's a weak base. And of course, the dissociation of water equation, as ever present, must be considered. So the CH3COOH situation there, we can add those because they are constantly changing, so we can put them in there. The hydroxide ions need to go in as well. And then we need to also get the H3O plus ions in there. So let's just count up and make sure we have 1, 2, 3, 4, 5, 6 again. So 1, 2, 3, 4, 5, 6 species again to rank. So how do we rank these species? Well, of course, water is always going to be in first place. Now, what comes next? After the water, we want to look at the sodium ions. So same thing again, you could say that you have 1 mole of sodium ethanoate to start with, therefore you get 1 mole of ethanoate and 1 mole of sodium ions. But similar to last time, the ethanoate in this case further reacts with water, so its concentration is diminished slightly relative to the sodium. So the concentration of sodium ions is slightly greater than the concentration of ethanoate. The ethanoate then goes on to form ethanoic acid plus hydroxide ions. And again, you could say that you have a 1:1 ratio between the ethanoic acid and the hydroxide ions. But because the hydroxide is supplemented from the dissociation of water, the concentration of hydroxide ions is greater than the concentration of ethanoic acid, which is therefore greater than the chloride hydronium ions in this case. So that excess of hydroxide ions here accounts for the fact that the system is weakly basic. So that's how you rank species in solution, and they're probably the 2 trickiest examples I could come across. There are many exam questions that you can try on that, but I don't want to go into every single one. They're probably the trickiest you come across. So that's my video for week 1 in review for aqueous systems. Now that we've introduced the idea that some of these systems, or a lot of these systems rather, affect the pH of the solution and make it weakly acidic or weakly basic, we can introduce the concept of weak acids and weak bases next week. Okay.